All right, Katie. So we've learned so far that the universe was in a very hot, very dense state, and then it began to expand. We've learned a lot about what happened in the first second. We've learned that the rules of the universe were different and are different when things are very hot and very dense. And we've learned that over the first couple minutes, things started to cool down and spread out. And as they did, we got the laws of physics that we know today.
Yeah.
Approximately.
Yeah, that's right.
We got the strong and weak nuclear forces. We've got the Higgs field. We've got gravity. And we've got electromagnetism.
Mm-hmm.
We've also gotten 2 episodes into this podcast, Dr. Mack, and we're like a minute and a half into the history of the universe. So today we're going to start to speed up a little bit.
Yes.
Hey, I'm John Green. Welcome to Crash Course, the Universe. On today's episode, the universe as we know it starts to come into focus. I knew Dr. Mack was going to start to walk me through what happened after the earliest moments of the universe, but I did not expect the connection between that hot, dense, early universe and today to be so intensely weird, and at the same time, so intensely logical. Like, the only thing that could have possibly happened mathematically happened. And that's what led us to photons and stars and us. And we can actually see that trajectory, which is just wild. But not as wild as knowing there might actually be a multiverse. All right, here's our conversation.
Okay, so up to this point, we've talked about the hot, dense early universe. We've talked about the sort of quark gluon plasma, how nucleosynthesis happened in the universe that brought together protons and neutrons and created the first nuclei. So, you can imagine that the place we are in the timeline, sort of as far as we've covered now, is there's a kind of hot sort of plasma of a lot of nuclei of hydrogen and helium mostly, and a bunch of electrons going around. Is where the cosmic microwave background kind of comes in. So we talked about the cosmic microwave background. It's the view of the universe as it was when it was a hot plasma. Okay, so we're still in that hot plasma stage. We haven't quite got to the place where everything's like cooled down yet, as far as the timeline we've covered so far. And so when we look at the cosmic microwave background from here, we can see kind of patterns in it. And we can see that when the universe was that hot, dense plasma, it wasn't perfectly uniform. Everything wasn't kind of perfectly spread out.
Oh.
When you look at an image of the cosmic microwave background, it looks kind of splotchy. Usually the way it's colorized is like blue and yellow or kind of patches or blue and sort of red patches, depending on how you do the colors. And it looks splotchy, kind of in the same way that like clouds on a sort of moderately cloudy day might be splotchy. So there are regions where it's more blue dots and regions where it's more yellow dots, or, kind of, it's splotchy, but not like a uniform fuzz. It's like clumpy and splotchy. Okay. And so that tells us something about how that matter, that kind of plasma of the early universe was clumped in the very early times. It tells us that there were places where that plasma was a little bit more dense and a little bit less dense, and that it had these little clumps all around it. And when I say a little bit more dense and a little bit less dense, I mean a very little. Those clumps are, when we look at the picture of the cosmic microwave background, it's basically just a uniform glow. In order to see the patchiness, we have to stretch the contrast so that we're seeing changes in the color or the temperature of that microwave light in like one part in 100,000. So we're really, really stretching the contrast in order to see that splotchiness.
Oh, so it's like almost uniform. Instead of being 1% not uniform, it's like 1,000th% not uniform.
Yeah.
Okay. Got it.
Yeah, it's 10 to the minus 5. It's like a tiny little bit of non-uniformity, but there is that splotchiness. So we can do something really interesting with that data, which is that we can take the distribution of temperatures in the cosmic microwave background. And we can interpret those as differences in density of that primordial plasma. And we can make a computer simulation. And we can tell the computer, okay, the places where it's a little bit more dense, those places have a few more particles, and the places where it's a little bit less dense, those have a few fewer particles, right? And you can set up a computer simulation where you give each particle a little bit of mass, and then you set the simulation running so that it has gravity, and so the little particles start to come together if they have a little bit more mass, and the places that are more dense kind of start to clump, and the places that are less dense kind of empty out a little bit. And you set that simulation running, and after a while, you get a picture that looks kind of like a web, that kind of looks like this sort of webby structure, like the foamy structure. And then that same pattern is the pattern of how galaxies are distributed in the universe. It's called the cosmic web.
No way.
Yeah. So
No. That's upsetting. It's upsetting that such a small variation led to galaxies, which I don't think of as small.
Yeah, well, the thing is that you just need a little bit of a seed, and then gravity will automatically make the places that are more dense more and more dense, and the places that are less dense will kind of empty out because things are moving away, toward the more dense regions. It's kind of rich get richer, poor get poorer kind of thing that gravity does.
Right. Okay, that makes sense.
If you give it enough time, then you'll automatically get the higher density regions will compress and pull in more matter. And so it was a very small variation in the very beginning, but those variations are actually on kind of large scales, because what we see in the cosmic microwave background, we're looking, this is like the distribution across the whole sky, and these variations are on order of like a square degree of angle on the sky. So these are, they're kind of big regions in the sky. It adds up to being quite a lot of matter at the time, even though we think of, the universe was very small then, or at least the observable universe was very small then. We think of it as being not a lot of space, but you can work out the scales, and it works out that the clumps that we see in the cosmic microwave background work out to be things that become sort of scales of clusters of galaxies. So what's happening is it's just that plasma, as it cools and compresses, it cools as the universe is expanding, and then the matter comes together through gravity, and that creates these what we call overdensities, these clumps of matter. And those clumps of matter are destined to become galaxy clusters. And it's kind of amazing that when we do these simulations, we can take just the data from the cosmic microwave background, just the data from this glow, from the afterglow of the universe, and that forward in time and see that those variations really are the seeds of the structure of all the galaxies in the universe, of how galaxies are distributed through the entire cosmos. It's exactly the same pattern. That's why things are not distributed evenly through the universe, because the universe was a little bit splotchy in that very, very early time in the radiation era, in the time when the universe was this hot plasma. It was already a little bit splotchy then, and we can see that directly. We can look right at it. We can look right at that radiation era, see those little splotches, and we know how gravity allowed those to grow into clusters of galaxies.
So we talked about the cosmic microwave background in episode 1 when we discussed evidence for why we know the Big Bang happened. And as Katie explained, if you look at a distant object, you're looking into the past because light takes time to travel. And looking far enough away, we're able to detect microwave light from the hot, dense, early universe, light from the Big Bang. This light is equally far away in every direction we look, and it's what we refer to as the cosmic microwave background. So to underline this incredible thing that Katie just explained, this light from the Big Bang is very uniform, but not perfectly uniform. There are small variations. And when we analyze the cosmic microwave background, these fluctuations we detect correlate to how galaxies are distributed in the universe, which is incredible, right? Anyway, you're about to hear me marvel at what Katie just told me, so I'll save you from hearing it twice. Wow. I'm definitely having that experience that I've had a few times talking with you where my mind is completely blown and I can't believe that I live in this universe. And I can't believe that there was a primordial soup, and I can't and I can't believe we got protons and neutrons, and then those protons and neutrons and electrons became you. That's weird. That is intensely, intensely weird. So
I'm going to make it more weird in minutes. just a warning there.
All right. Well, I'm already there. I'm already in the mind blown place, which is an exciting place to be. I love being here. It makes me anxious, but I like it. Do we know the why of why there were these small inconsistencies, why there was this slight splotchiness in the early universe?
Okay, so we have a really good theory of why. There are things we don't know. There are still arguments about whether this is the correct interpretation, but we think that it comes down to the process of cosmic inflation. I'll just recap. We think that the universe went through a very, very, very rapid expansion in the first, tiny, tiny fraction of a second, like a trillionth of a trillionth of a trillionth or something of a second, 10 to the minus 35. There was this very, very rapid expansion, and there are a couple of reasons we think that happened, and one of them has to do with the fact that the cosmic microwave background really is very uniform, which suggests that whatever the primordial state was, it was very, very uniform. And we don't have a reason for that to have been the case. And with the standard kind of thinking of the universe starting with a singularity and then going on from there, it wouldn't work out that it would be that uniform. So we think that this cosmic inflation kind of basically stretched out the universe so much that it zoomed in on a very small part of the earlier universe, where that small part might have been already kind of about the same temperature everywhere. It's kind of because it's stretching out everything so much, our entire observable universe is contained within what would have been a very, very small patch of, the whole universe before that cosmic inflation happened.
Oh, no. So there was a lot of other space that is probably beyond our observable universe.
Yeah. So if cosmic inflation happened, it implies that we are a very small part of a very, very huge universe, or multiverse, if you want to think about it that way.
Oh, no. Oh, God.
But all of that stuff, all that other stuff is so far away from us now because of that rapid expansion that it can't possibly affect us. That might be some comfort.
Yeah. That's a little bit of comfort. I mean, it's good to know that, we won't be attacked by those other universes or whatever. But it's more just a feeling of if that was a tiny part, a relatively uniform part of a much, much larger soup, that implies that our universe, which is unfathomably large, is not nearly unfathomable enough.
Yeah. And there are theories that maybe that larger space is just constantly inflating and just it's stretching and stretching kind of forever. It's called eternal inflation. And in our bit of universe, in our observable universe, our part of the universe stopped that super inflated expansion. It shifted, the super accelerated expansion stopped, and now it's just regular expansion. And so we got this little pocket of universe that's kind of able to have, stuff in it as the universe is kind of in its normal expansion phase. There might be other pocket universes in this much larger space that are creating their own little hot Big Bang phases where the universe has, it fills with plasma and then cools down and then grows galaxies and so on. So there might be all these little pocket universes that had their own inflationary phase and then the hot phase and then the matter phase. And in fact, you said we couldn't be attacked by any, which is true, but there are some hypotheses where maybe our little pocket universe and another little pocket universe kind of dropped out of this inflating stage close to each other and could bump up against each other.
Mm-mm. Yikes.
Well, so, I mean, the observational effect would be that there would be a little spot, a little bruise in the cosmic microwave background, and people have looked for that and haven't seen it. So, probably.
Okay. But it wouldn't be the end of me.
It would not annihilate us all, no. Anyway, yeah, so if inflation is indeed what happened, then the process is that there was this very, very rapid expansion, and then for whatever reason, that expansion stopped happening that rapidly, and the kind of field that was responsible for that very, very rapid expansion would have itself sort of decayed into radiation, which is what would have ignited that hot phase in the very early universe. Then that radiation then turned into, quarks and gluons and all the particles and the plasma that we see in the cosmic microwave background. So there's this kind of like several step process that we think happened to create the universe we have to date. But the way that that connects with those little variations, those little density variations, is that we think that as inflation was happening, and especially as it was ending, the fluctuations in the energy field driving inflation, we call it the Inflaton Field. So it's not a very creative name, but there was inflation. It was driven by the Inflaton Field. I know.
It's terrible.
I know.
It's like unobtainium. That's how bad it is. I don't want to criticize the person who came up with it. They're probably still alive. They're probably listening to this podcast, but like that's not a good one.
And it's frustrating too, because whenever you're writing a paper about these things, like the spell checker is constantly taking issue with the word inflaton because it's like, didn't you mean inflation? I'm like, no, that's the concept. We're talking about the field. Like it's anyway. So the Inflaton Field would have been a scalar field, which is like the Higgs field, where it's a field with some value everywhere, right? And it evolves according to a potential, which is a concept where it kind of tells the field how to change. But we think that basically that field, it was a quantum field, and it was like wiggling around due to quantum uncertainty. Just that all fields wiggle around due to quantum uncertainty. That's part of quantum mechanics, the way that a particle can be in kind of two places at once, or you don't know where it is or how fast it's moving at the same time. There's this quantum uncertainty. So we think that field was kind of wiggling around with quantum uncertainty as inflation was happening. And that caused some parts of the universe to inflate a little bit more and some parts to inflate a little bit less because of that quantum uncertainty.
Okay.
And if that's true, it would create exactly the kinds of density fluctuations that we see in the cosmic microwave background. Those density fluctuations can be traced back to the fluctuations, the wiggling of this quantum field, the inflaton.
Wow.
And so now we have a direct line from quantum uncertainty, from like these random fluctuations of a quantum field, to the features in the background light of the universe, the direct view of that hot plasma of the Big Bang, to the distribution of galaxies in the cosmos. It's wild.
That is wild. So there are equations that can tell us that this inflation with quantum wiggling would lead to a cosmic background radiation that looks about like the cosmic background radiation we see. And then there are equations that tell us that the cosmic background radiation we see would create approximately the clumping of galaxies that we see today.
Yeah, the large-scale structure of the universe.
I mean, that is... Wait, what do you call it? The large-scale structure?
The large-scale structure of the universe, yeah, the cosmic web.
That's good. The cosmic web is good. The large-scale structure of the universe is good. That's really beautiful. I mean, it's a little terrifying, but it's also just gorgeous that, like, it's still so weird to me. And I know that this is partly a function of my imagining, because, like, I'm applying language and, like, my high school chemistry and physics and whatever to this. And of course, like, language and reality never have a one-to-one map. But, like, it's so weird to me that what happened was protons and gluons. And then that led to us. Like, that's so mind-blowing. So yeah, there were some protons and gluons, and then there was, like, us. Like, I'm at least partly made out of a slightly cooled plasma soup from 16 billion years ago, which I find to be an encouragement. My protons will be around a lot longer than I will, and it's nice to know they'll still be doing that vastly complicated, mind-bendingly weird proton stuff long after I'm gone. But I will, of course, be gone. And that's why there's life insurance. With Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options offer same-day approval and avoid unnecessary medical exams, and with Policy Genius's licensed and award-winning agents and technology, it's easy to compare life insurance quotes from America's top insurers. Make things a little easier for those who will still exist after you don't. by checking life insurance off your to-do list in no time with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. Policy Genius. Protons are complex. Life insurance doesn't have to be. That's not their tagline, but I think it's a good one. I guess, like, of all the things that might have happened, the only thing that could have happened, which is, like, maybe that's the way I need to think about it, but it is very weird to me that all of this was set up so early.
Yeah, I mean, it's evolution, right? Like, one thing happened and led to another and led to another and led to another. The amazing thing is that we can see that whole evolution, that we can see so much of that story very directly because we can look into the past with astronomy. I mean, we're making inferences about cosmic inflation. There have been other theories about what caused those fluctuations and stuff. Inflation is the most accepted, but there's some uncertainty there because we can't see inflation specifically. But we can see the cosmic microwave background. So we can directly see, very, very directly look at the universe as it was about 380,000 years after whatever the very first moment was. And I use that term. I don't like to say after the Big Bang because the term Big Bang is a little bit nebulous. Sometimes it refers to the hot Big Bang, which is the whole period when the universe was hot, that radiation era. And some people refer to it as the first moment. So I try to not get those terms confused, but we can directly see back to about 380,000 years after the beginning. And we can make inferences through, like, really good inferences through both theory and experiment down to, like, picoseconds or something like that. And then we can infer through theory down to this 10 to the minus 35 seconds or whatever when the cosmic inflation happened. And then with, direct observations, we see the whole timeline after that with astronomy, because we can see the cosmic microwave background and then we can see very early galaxies and how those have changed over time by seeing the more recent stuff compared to the older stuff. So we can really watch that evolution very directly.
So we can compare early galaxies, like especially now with the JWST, we can compare early galaxies to more recent galaxies?
Yeah, and there's some wild physics in why we can do that. I think I touched on this in the first episode, but the reason that we can see details in very, very early galaxies has to do with the fact that a galaxy of the same size, farther and farther away from us, at some point starts to look bigger than one that's closer. But it's because, like, the most distant galaxies that we can see, the ones we're seeing with JWST, they were actually closer to us when their light left them, because the universe was so much smaller than some of the nearer galaxies were when their light left them. It's not a straightforward thing. Like, galaxies at different distances now, the farther away it is now, the longer its light left us, but the light might have left it at a time when it was actually closer to us than it is now. It definitely was closer to us than it is now, but it might be closer to us than a galaxy currently closer to us than it is, was when it happened. The tenses get complicated here.
Yeah, I was going to say this becomes a real tense challenge, but I think I get it. Basically, the universe was smaller, and so those galaxies appeared larger to us because they were closer to us then, because the universe was smaller, and now the universe is much bigger, but the light takes so long to get to us that it's as if the universe were smaller.
Yeah. The picture of that galaxy took up more of the sky than the picture of a galaxy that's, currently a little bit closer to us would have taken up because the universe was so small at the time.
So we've got this cosmic web that we can see, and we understand that because of gravity, things started to clump together more and more over time. But, like, what are they? What is that? What are the clumps?
In the timeline that we got through so far, we got to the point where we had the first nuclei, right? So we had that hot, dense sort of the whole universe is a nuclear furnace. It created hydrogen and helium nuclei and a smattering of other elements. Okay, so we're still in that plasma state, and there are places where the plasma is a little bit more dense, places where the plasma is a little bit less dense. Those things are destined to turn into galaxy clusters and so on. But at the moment, it's just this plasma. So what happens is the universe gets bigger and bigger, and so that plasma kind of spreads out and cools. And so that's just kind of, as you make a gas bigger, it gets cooler. The atoms are farther apart. That's kind of a straightforward thing. And so the universe starts to cool. And so there's a transition at some point where, when you're still in that hot plasma state, light bouncing around between the particles gets kind of trapped. It's like it's so dense and so hot that photons can't travel very far without bouncing off of particles. And so the whole universe is kind of glowing, and the light is kind of bouncing around and kind of trapped. It's kind of just this really bright sort of space. But as the universe expands a little bit, then the particles get far enough apart, the electrons and the nuclei get far enough apart that photons can move sort of more freely through the universe, and that light can kind of disperse. This part of the timeline is very similar to going from the center of the sun outward into space. So in terms of the timeline, it's very, very much like going from the center of the sun out to space, in the sense that you go from a space where everything's hot and dense and there's, nuclear reactions happening, you're fusing hydrogen and helium, and then you get farther out, and the sun gets a little less dense. I mean, the sun doesn't have a surface. It just kind of gets more diffuse. It's a ball of plasma. It just gets more diffuse as you go toward the outside. And at some point toward the edge, you get to the point where light can move out of the sun, right? I mean, you might have heard this statistic that like a photon produced at the center of the sun can take like 10,000 years to reach the edge. This is this very effect where the photons are kind of bouncing around between the particles. It takes a long time for those photons to like diffuse outward toward the edge. So the light that we see from the sun right now, it took 8 minutes to get from the surface of the sun to us, but it might have taken 10,000 years to get from the center of the sun to the surface.
Wow.
Because the sun is so dense and it's this hot plasma. And that's what was happening in the very early universe in this time. Around, first few 100,000 years of the universe, it was this hot plasma like being in the center of the sun. But then as the universe expanded, it's like we're moving toward the outer edges of the sun. And at some point you get toward what in the sun is called the photosphere. And in the solar photosphere is where a photon can now escape into the universe. It's no longer kind of trapped bouncing around anymore. And so when we look at a picture of the sun, we're seeing the photosphere, because it's kind of like we're seeing the edge of where the light can start to move to us. And so the cosmic microwave background is basically the photosphere of the early universe. So it's a transition that happened in time, but because time and distance are so are connected in cosmology, it really is very much like a distance too. So we call that sometimes the surface of last scattering.
Oh, that's beautiful.
Yeah.
The surface of last scattering. Oh, gorgeous.
And it's amazing because it is a surface to us. I mean, it's a time, but it's also a surface because we're looking back at it. And as we look back, we're looking farther back in time. And so we're really seeing that transition, that surface. And so the cosmic microwave background is a picture of the surface of last scattering. It's the picture of the photosphere of the early universe.
So it's both the surface of last scattering and the time of last scattering.
Yeah.
Wow. That's a great title for a novel, by the way.
Yeah. Yeah, it would be, huh? It's a beautiful image that we are looking back into the early universe as though we are kind of looking back through layers of a star, back to the time when, the universe was like the center of a star. So the surface of last scattering marks that transition from the universe being really just this glowing plasma where if you were sitting in the middle of it, all of space would just be bright, to a time when there would be brightness at the edges, but light could travel in between. Like you wouldn't be engulfed in fire. Right? If you were after the surface of last scattering, it might not be a pleasant universe, but you would not be immediately in flames. So Same way, like if you're outside the edge of the sun, it might take a minute, right?
It would still be pretty hot, pretty dense.
Yeah.
Pretty miserable from a human perspective, but better than being right in the middle of the sun.
Exactly. Yeah. So a couple of things are happening there. One is that those photons are able to move around because the universe is reducing in density, but also because the universe is getting less dense and cooler, it becomes possible for electrons and protons to find each other and bond. So before that, it's just a hot roiling plasma. A plasma means that the particles are ionized, right? So the protons don't have any electrons around them. Electrons are flowing freely. Same with the helium nuclei. They're, ionized helium, ionized hydrogen, electrons. But once the universe cools enough, then the electrons and protons are able to come together. The electrons and the helium atoms are at some point able to come together. And so you start to have neutral atoms, and this is the first time that neutral atoms occur in the universe. It's a kind of unfortunately named moment because we call it recombination. It's not the right term because this is the first time this has ever happened. So,
Right. They're combining for the first time.
Yeah, they're combining for the first time. It's called recombination because of some historical thing around when we talk about plasmas and things evolving later in the universe. There's a process called recombination where something becomes neutral again after having been reionized. But anyway, it's called recombination, but it's this first moment when neutral atoms are able to form. And so that recombination era, that moment when the first neutral atoms form, that begins what we call the dark ages of the cosmos.
Okay.
And the reason it's called the dark ages is because now the primordial plasma is cooled down, but there's no stars yet. The universe is just hydrogen gas, mostly with a little bit of helium in it. And it's just cooling. It's just gas cooling down, and the universe is expanding. And at the same time, gravity is still pulling together clouds, right? So you have these clouds of cold gas, and those clouds are starting to condense. So the Dark Ages goes on for a while.
Wait, like 2 seconds or
No.
like 10 years?
No, like millions and millions of years.
Oh, great.
Yeah.
Okay.
Yeah.
Hey, we cannot have 10 to the negative 35 seconds and then like 10 to the negative 15 seconds being a while and then have like several million years be a while.
This is the thing, right? Like the time scales get weird, right? Because you count it based on how much is happening. And you can have millions of years of cold hydrogen gas, and not a lot is happening in that cold hydrogen gas.
This is great for us, Katie, because suddenly it's looking like we can get through this season. I'm starting to believe in us. We just skipped way ahead.
Yes, exactly. Yes.
All right. So we've got these millions of years where there are some neutral atoms, but it's just clouds of gas slowly clumping together, slowly getting colder.
Yeah, exactly. So this is the cosmic dark ages, and the physics of it is very simple. It's there. You can write down equations for gas cooling, and it's doing that. But over time, because we had these little variations in density, some of the clouds of gas start to get a little bit more dense than other clouds of gas. And so...
Whoa. If we'd never had these little variations in density, if our observable universe had been entirely uniform, there never would have been stars and galaxies?
I don't know that they're never... Well, you would still have fluctuations just based on the random movement of particles.
Oh.
So eventually something would happen, but it would happen differently and would take a lot longer.
Okay. That's helpful and a little mind-blowing.
Yeah.
Okay. All right. So we're only here in this current state because of those early quantum fluctuations that came along with inflation.
Yes. Yeah.
Otherwise, I wouldn't be here.
Yeah. Yeah. This is why there is structure in the universe in the way that we know it.
Great.
Yeah.
Okay.
Yeah.
I'm gonna not panic. I'm just gonna listen.
Okay. Okay, so these clumps of matter are starting to come together. And so what I've told you so far is that these clumps of matter are made of gas, of the cold hydrogen gas mostly. I've left out a really important piece, which is dark matter.
Oh, boy.
And dark matter is really important to this story, actually. So I think that we're going to get more into dark matter and dark energy in a few episodes because there's a lot more to say about those things. But I'll just tell you two things about dark matter right now. One thing is that we think there's way more dark matter in the universe than regular matter. So dark matter is something that seems to be sort of invisible stuff that has mass, it has matter, it comes together with gravity, but we can't see it. We're pretty sure that most of the matter in the universe is dark matter, like 85%. And so then the reason that we call it dark is because it seems to be invisible. And when I say invisible, there's an important caveat. There's an important thing about invisibility that we have to cover, which is if I say invisible, what I mean is that it doesn't interact with light. It doesn't reflect light. It doesn't absorb light. It doesn't emit light. And light is just electromagnetism, right? So light is photons. Photons are what mediate electromagnetism. And the important thing about something that doesn't interact with light is that if you can't see it in that specific way, it also means you can't touch it. Because whenever you touch something, what you're really doing is you're pushing your electrons against the electrons in the other thing. And it's really electromagnetism that's making things feel solid. Electromagnetism is what makes atoms hold together with other atoms to make molecules and things. And it's the repulsion that means that you can't pass solid things through other things. That's really electromagnetism. It's electrostatic repulsion. And so if dark matter doesn't interact with light, it's not only invisible, it's untouchable, which means that it can pass through itself and other matter. It doesn't, collide with things. It doesn't like smash together and heat up the way that gas does. It doesn't feel solid. And so that's important to this part of the story because when inflation created those density fluctuations, the places that are a little bit more dense, not only do they have more hydrogen gas or plasma, they also have more dark matter. And so when this gas is starting to be able to fall together, because there's now, the gas is cooling and it's starting to cool, it's starting to be able to like interact via gravity rather than just be, sort of bouncing around in the plasma, the gas is starting to fall into the clumps of dark matter that were sort of set down in the initial fluctuations from cosmic inflation. And so because clumps of dark matter don't like collide with each other, there's no pressure, those clumps of dark matter can just kind of fall together in a way that gas has more pressure. Gas is kind of like, it bounces a little bit more and the dark matter doesn't. And so it's able to create these gravitational wells that the regular matter can fall into, and it helps the matter come together to form the first structures.
Okay, so dark matter doesn't interact with light. It's not touchable.
Yeah.
It's not visible, but it has mass, and so it does interact with gravity.
Yeah, and so it feels its own gravity, and regular matter feels the dark matter's gravity, and dark matter feels the gravity of regular matter. And so because there are clumps of dark matter now that were set down by those early seeds of structure, those clumps of dark matter are starting to pull in gas. And so that cold gas is starting to fall together, aided by those clumps of dark matter. The clumps of dark matter are kind of providing extra pull to get that gas together.
And as it comes together, presumably it becomes more dense, which means it becomes more hot.
Yes. And this is where we start to get the beginnings of stars and galaxies. Because that gas, as it's coming together, it can compress and it can start to heat up, and you can get these balls of gas that can start to get so dense in the center that they can start to have nuclear reactions in the center. And that begins the epoch of the first star formation. This is how the universe goes from the Dark Ages to what we call cosmic dawn.
That's a good one, too.
Yeah, I like that one a lot.
It's very good. It's not as good as the what of last scattering?
The surface of last scattering.
Oh, the surface of last scattering is...
I know.
in this cosmic dawn, the whole universe was originally a gigantic nuclear reactor. Then things got cold and dark and not that interesting. And then as the gas started to come together with the help of dark matter, we got these individual nuclear reactors called stars.
Yes. Yeah. Yeah. And they formed in, clusters, in clumps, in these early galaxies, all that matter having been brought together by the dark matter. But it allowed for the first stars to ignite. There's still a lot of uncertainty about what those first stars looked like. Stars forming today have a much different environment to form in. There are all these heavier elements that are around. And because of that, when the gas to form a star today is coming together, that gas has to cool in order to keep compressing. Like if it's too hot, it just kind of bounces out, right? It stays diffuse. But in order to really, really compress enough to make a star, it has to cool a little bit to fall together more, right? The idea is that if something's too hot, it's too puffy. If you want to compress something, you have to cool it. Then as it's compressing, it gets hotter and hotter. There's a kind of balancing act that has to happen. But with modern stars, a lot of that cooling, it happens through like dust. It sort of causes like vibrations in dust, and then that radiates some energy, and things cool down through molecular interactions, through dust. All these different processes can allow some of that energy to be lost, and allows some of the sort of heat of this clump of matter to radiate away, and that allows it to cool and compress and compress. In the very early universe, we had this primordial gas, which was just hydrogen and helium, and just a tiny amount of helium. And it's harder. There are fewer avenues for cooling that gas. And so there are still these debates about, maybe the first stars were like hundreds or thousands of times the mass of the sun. Maybe they were super, super massive because, in order to get enough matter together to create those first nuclear reactions, maybe you just needed way more matter because you couldn't cool it down if it was too small a clump. And so you had these really big, super massive stars. And there's still debate about that, but we think they probably were more massive than the present day stars. And so those earliest stars probably looked quite different to the stars today. And it was harder to form them because it was harder to get that gas together because it didn't have all these cooling mechanisms. But somehow, whatever happened, some of these stars came together. The gas was able to compress and clump, and the first nuclear reactions were set off in the centers of these stars. And that is what sparked what we call the cosmic dawn.
Wow. And so were there immediately planets, or did planets happen after that?
So planets require heavier elements.
Okay, and so these nuclear reactions, part of what they did was make elements other than hydrogen and helium.
Yeah.
So part of what they did was make those heavier elements and kind of spit them off.
Yeah, there's this whole story about what we call it polluting the intergalactic medium. So
that's good too. I feel like things are getting much better in terms of names.
Yeah. So as the star is burning hydrogen in the center into helium, depending on the mass of the star, it can burn heavier elements, and it could create, carbon and oxygen and nitrogen and so on. And then those elements will be scattered when the star goes supernova. And so you have this process of stars forming and then exploding and scattering their elements around, and those elements can then become part of the protostellar clump of gas for the next star that forms, the next generation of stars. And you go through several generations of this to create a universe that's full of the kinds of elements that you need to make things like planets.
So this takes many millions of years, or even billions of years, to have these successive generation of stars that, as they explode or implode, I don't really know what a supernova is, but like as they do whatever they do when they die, then they spit off carbon and oxygen and nitrogen and the stuff that is in our atmosphere now.
Yeah. So the timeline there, it's kind of constrained. So because we know that the surface of less scattering, cosmic microwave background, that was 380,000 years after the beginning. And we know that there were full-on galaxies within about 400 million years. because we can see them now with JWST. So it was the first couple 100 million years when these first stars were starting to form and, creating the first galaxies. And then those first stars, because they were supermassive, they were probably very short-lived. Or it depends. There are certain models where they can live longer. But generally speaking, a very massive star is the shortest lived. It burns through its fuel more quickly, and then it goes supernova early. And so you could have stars that were very, very massive that would have lifetimes of a few or tens of millions of years. And then, so you can go through generations pretty quickly that way.
I mean, not that quickly from my perspective.
But, on a cosmic scale.
Right, right.
We've shifted from thinking about, picoseconds to thinking about millions of years. And this is a weird thing to do, but as a cosmologist, you got to kind of be flexible in your time scales as you go to different epochs of the universe. Yeah, so we know that there were, fully evolved galaxies within the first 400 million years.
Wow.
Or maybe even 200 million years, depending on what we think of the current observational sort of limits. And so somewhere in that first couple 100 million years, the first stars formed, exploded, next stars formed, exploded, and clumps of stars formed and galaxies. Those first galaxies happened, as far as we know, very, very quickly.
Wow. And it seems like every generation of star is a little bit easier to make. Is that right? Because there's a little bit more heavier elements around to kind of force that cooling that leads to the heating?
Yeah. I mean, specifically, the very first stars are, I would say, the hardest to make. Mm-hmm. And then as you have some heavier elements, it helps the cooling processes. And so it becomes easier as you go.
Wow. Just like life. It's so hard at the beginning. You don't even know how to do anything. And then it gets a little easier. It never gets easy.
Right. Yeah.
It does get a little easier. Wow. I'm going to treasure so many of these terms and concepts. I have to ask you, do you still feel awe?
Yes.
When you think about this stuff?
All the time. Yeah, absolutely. I mean, I don't know if you can hear it in my voice, but it's amazing. I mean, it's amazing to think about these huge forces and these incredibly violent and important processes that happened throughout the course of the cosmos, but it's also, I mean, it's awe-inspiring that we can even tell this story, that we have so much information.
Right.
We're within, the first sort of 10% of the universe that we've talked about so far, right? But we have such a coherent story about all of that. We know how it all fit together so well, and it all kind of follows mathematically from every previous point in a way that is beautiful and confirmed by experiments and observations, and we can look at this stuff and see the cosmic timeline. I mean, yeah, it's incredibly awe-inspiring. It's amazing. And it's amazing, when we see these images of early galaxies from JWST and things like that, we're looking at, some of the first things that ever existed in the universe. I mean, we're just looking at them.
Yeah. But there's also, with awe, there's an element of being overwhelmed by the beauty and, really feeling small in the face of something large.
Yeah.
I mean, I think about this in a religious experience context of the definition of awe. There was this famous theologian who said, who talked about this concept of the numinous, which was encountering the radical other and feeling very small before it, and that feeling of awe has a lot of wonder and thrill in it, but also has an element of terror and fear and really feeling your size in the face of the universe's forces, however, you construct that. And I have to say, when you talk, I do feel both. I feel the wonder, I feel the thrill of it, but I also do feel a tinge of what I keep referring to as, oh boy, almost like an overwhelmedness.
Yeah. Yeah. No, I get that for sure. And sometimes when I'm thinking about this stuff, I get this feeling of standing at the edge of this giant chasm, and just there's this huge space that I can't quite conceptualize, that I can't fully understand, but I'm like right at the edge of it. I'm looking down, and I'm trying to see to the other side, and it's a little bit frightening to think about just that vastness, and the power of it.
Mm-hmm.
Yeah.
We started this episode in the first few minutes of our universe, and we're ending it millions of years later. As Katie mentioned, cosmologists need to be flexible with timescales. I'm eager to continue our conversation because I'm starting to be able to understand, how we got from the first picoseconds to now, but I'm still pretty overwhelmed, to be honest. It's just unbelievable to me that we can conceptualize the hot, dense, early universe and be able to connect the dots all the way to stars forming millions of years later. As I said earlier, of all the things that might have happened, the only thing that could have happened, and it's a thrill to start seeing why, even as it also has me asking some pretty serious questions about free will and determinism. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, and mixed by Joseph Tuna-Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.